Hello and welcome to another topic in chemistry. Go ahead and start setting up your focused notes. This is the first day of our new unit of a topic called stoichiometry. So that's how you say this. So stoichiometry, it's actually from a couple Greek words meaning measuring elements. So that's what where that word comes from. Go ahead and fill in whatever date it is that you're taking these notes. And the essential question we're going to answer in today's lecture is, how do I interpret balanced equations in terms of moles? So there's that new chemistry word we learned in our last unit. And how do I write mole ratios from balanced equations? So this unit is cool because it brings together a bunch of different little things we've talked about earlier this trimester. And then you can start to see some practical applications of some of those topics as well. In today's video lecture, you will know that you should write something down if it's in this kind of lavender color. So, other colors like blues or purples or other random colors, those are things that I just want to talk about and help you listen and explain things. But to kind of guide your writing focus notes, the only things you need to write down are the things that are in this kind of lavender or grayish purple kind of color. All right, so with that guideline, let's go ahead and get started. All right, so the first thing is, okay, wait, Swickle, what is this unit? So this unit is all about looking at a balanced equation. What information can you get from it? This is the unit that explains why we learned how to write compound formulas. Why did we learn how to do this thing called dA? Why did we learn how to write equations and write balanced equations? And why did we learn how to predict products? All of it comes together in this unit called stoichiometry. And I get really excited about this unit because I think it's really, really interesting and practical to start seeing why chemists need to know all this kinds of stuff, other than just being good at chemistry things. Like, what do we do with all this stuff if we're good at it? That's what this unit starts to show. So remember when we learned about equations? It was a couple weeks ago. So if I show you a reaction between nitrogen and hydrogen like this, so I say N2, because nitrogen's diatomic gas, plus H2 gas, because hydrogen's diatomic, produces NH3 gas. Is this an accurate representation of the reaction between nitrogen and hydrogen? Think about that. No, it's not. Why not? What's wrong with this? Yeah, maybe you notice that, oh, here I have two atoms of nitrogen, but only one atom of nitrogen here. Where did that other nitrogen go? That seems weird. Here I start with two hydrogens and suddenly I have three hydrogens. Wait a second, that seems weird. That seems like magic. That's this idea of the law of conservation of matter. Matter can be changed, but you can't create it. It's not okay that we suddenly have hydrogen more or destroy it. It's not okay that we suddenly have less nitrogen. So remember, when we write equations, that's that idea of balancing it. So go ahead and add these, or you can write it down if you want to, or just look at this. So now when I put numbers in the front, those coefficients apply to anything behind it and it multiplies. So I still just have two n's, but now I have two n's on this side too. But now I have 3 times 2, that's 6 h's, but 2 times 3 is 6 h's here. So that balanced equation is super important for what we're learning in this new unit, because otherwise you will think that there's just one molecule of this, one molecule of this makes one molecule of that, and that is not true. And so remember that a balanced equation is important for the law of conservation of matter. All right, go and pause the video, write a level 1 question. State the law of conservation of matter would be a great one, or make up your own. Remember, there is that guide on Schoology that you could use to help you find high quality sentence starters at the different levels. Pause the video if you need to, come back when you're ready. Let's continue on. All right, so the whole point of stoichiometry is knowing how much of something it takes to make a reaction happen. This is something that real chemists would need to figure out, right? Rather than someone telling them, oh, measure out this much in the lab and then make this much. That's not reality, right? So the practical applications of what chemists need to know is shown in this kind of calculation called stoichiometry. How much do I need to, if I want to make a certain amount of product, how much reactant do I need to start with? I can calculate that instead of randomly mixing it together. So if I'm looking at an equation, what in that equation tells us how much of that element or that compound we have? So if I'm looking at a balanced equation, what tells me how much of that element or compound we have? Yeah, it's the coefficients. And it turns out that the units of those coefficients in a balanced equation are moles. So stoichiometry shows, why did we learn about this vocab word called moles? It's because that's how we know the relationship between how much I start with and how much I end with, or how much of reactant one do I need if I have this much of reactant two to make this much of react or product, whatever. So that idea, that mole comparison, is the new big thing from this unit. So, because moles are so important, guess what comes back? Yay! Ready? Why did Avogadro come to visit Minnesota? Yeah, he wanted to see the mole of America. He heard it was a molesing and he just had to check it out. All right, and then what place did Avogadro win at the science fair? All right, now think about this one. This one's tricky. Because remember, people didn't believe that Avogadro knew what he was talking about. So there was a lot of people that kind of made fun of him, right? So what place would he maybe have won? Because he was pretty smart. What place would he win at this science fair? He got honorable mention. Good job, Avogadro. Sorry, we don't believe in atoms. That's what people told him. All right, so moles come back. That's the point of that silly little mole jokes. All right, coefficients. The coefficient in a chemical equation tells us mole ratios between the parts of a reaction. So, for example, if this balanced equation, 2 water produces 2 hydrogen molecules plus 1 oxygen molecule. The mole ratios are comparing the coefficients to any other coefficient in the balanced equation. So if I wanted to compare water and hydrogen, the mole ratio would be 2 moles of water for every 1 mole of hydrogen. And I realize you could simplify that to 2 or to 1 and 1, but I recommend keeping mole ratios, the numbers that match the balanced equation, to remind you where they came from. Mathematically, yeah, it is a 1-to-1 ratio, but 2 to 2 reminds you that that came from the balanced equation. Okay, now you do the same thing. Write the mole ratio for water to oxygen. Go ahead and take a moment to do that. What would it be? Same format as this. What would it be? Yeah, 2 moles of water for every 1 mole of oxygen. Because remember, if there's no number written there, that's really a 1. Okay, do one more between hydrogen and oxygen. All right, you got it? So 2 moles of hydrogen for every 1 mole of oxygen. This is the key to every single stoichiometry problem, and I call this the switch over step, because this is how you switch over from one chemical to a new chemical. We've never been able to do that before. We've been able to switch over from, like, water, we could go to grams and moles and liters and milliliters, ounces, lots of things like that, but it would all be water. What we can do now is we could use any unit related to water, get it to moles, and then switch from moles to hydrogen and get to any other units related to hydrogen. That switchover step is the key, this new big idea for stoichiometry. All right, go ahead and do a level 2 question so far. Pause the video, think about what we've done so far, write a question, come back when you're ready. Okay, so now we have a new conversion factor. I can use the balanced equation to go from moles of one thing to moles of another thing, and that is super awesome in chemistry because it's more practical. So the switchover step is going to look like this. Some given, just like we've always been using, and that might be in moles. And then if you're just doing the switchover step, you would have start with moles, you would have moles of that thing on the bottom and moles of something else on the top. So your conversion is moles to moles, but of different chemicals. That's what makes this the switchover step. So you fill in these blanks by using the coefficients from the balanced equation. So what's the ratio of chemical A to chemical H? The mole ratio switchover step. All right. So let's see what that looks like. So when you go from moles of one chemical to moles of another, that's called the switchover step. And that's the crucial part for surviving stoichiometry. So let's go ahead and practice this. So you can put this either in your notes or on the output page next to your notes. But here's what it looks like. If this was my balanced equation, 2 waters produces 2 hydrogen plus 1 oxygen. If I ask you, 2.6 moles of water is what I start with, how many moles of oxygen are produced? Well, this is still a DA problem. So start with your given 2.6 moles of water. So start with that. But then I want to get to moles of oxygen. That's how I know I need that switchover step, where I compare moles of what I have to moles of what I'm trying to get to. So 2.6 moles of water is my given. So moles of water, and it's 2, that comes from the balanced equation. And then 1 mole of oxygen, that comes from the balanced equation. And then you work it out, 2.6 times 1 divided by 2, you get 1.3 moles of oxygen. So moles of water cancels. I'm still at moles, but now it's moles of oxygen. So I've switched chemicals. So now I can compare something that I started with to something that I'm producing, a new skill, right? Still stoichiometry or still DA. And the new thing that makes it stoichiometry is this mole to mole ratio. Well, how about this? What if I start with 2.15 moles of hydrogen or being produced? That's what I know. I measured out 2.15 moles of hydrogen. How many moles of water did I start with? Maybe I need to know that for my lab notes for future reference. I measured the product and then I'm like, wait a second, how many moles of water did I use to make 2.15 moles of hydrogen? So my given 2.15 moles of hydrogen, I get the balanced equation. There's 2 moles of hydrogen, that goes on the bottom, and there's 2 moles of water. That's my switchover step. So the switchover step is moles of something to moles of something else. Now I realize, look, moles of hydrogen cancels, but so do the 2's. You still do the setup though, because that's where moles of water came from. Without it, you wouldn't be able to show where moles of water came from. So it's still 2.15 moles, but now it's water. So this shows you where hydrogen went, it canceled, and how you ended up with water. That is the DA with the switchover step. This is what makes it stoichiometry. Okay. But the next part of this will be, well, wait a second. Okay. So that's maybe interesting, but stopping at moles is not very useful. But there's some stuff we know related to the moles other than just mole to mole ratio, right? So molar mass is another thing we could do. What it means is how many grams of A are in 1 moles of A, and A would be some chemical, a compound, an element, diatomic element, and you get that from the periodic table. That's molar mass. And then mole ratio is where we connect moles of one thing to moles of something else. And that comes from the balanced equation. So now what I can do is I could maybe start with grams and get to moles. And then I could be at moles of A and switch over to moles of something else. And then maybe go back to grams. That's the idea of what we're going to start doing next. Okay, so solving stoic problems, you're going to know it's a stoic problem because the given will be one chemical and the question will be a different chemical. That's your clue that you'll need to do a stoic problem with that mole switchover step. So the 3 big things you need to know about stoic are this. Stoic problems need a balanced equation. Without it, all your mole ratios will be 1 to 1 to 1. Now, that's true sometimes, but not all the time. So make sure you start with a balanced equation. So anytime I give you a stoic problem, first go and check to make sure you have a balanced equation. Then every stoic problem has that thing called a switchover step, and the units need to be in moles. So if your given is not in moles, use other mole conversions, molar mass, molar volume, Avogadro's number, whatever other conversions we know to get to moles. Then you do the mole-mole ratio from the balanced equation, because that was the first thing that you did. So that's kind of an overview of what we do for stoic problems. Now we need to start doing a bunch of examples to see if this makes sense. Before that, though, do your level 3 question to finish off today's notes. I see this is a typo. This would say question. And again, level 3 is more like interpretive, creative. Predict a time when we would need to use stoichiometry. That's a great level 3 question to kind of wrap your brain around, why do we care about this stuff? All right. So that does bring us to the end of our notes for today. So you're going to finish any Costa questions if you didn't write them already, and you're going to write a summary. Go back to your essential questions, answer those essential questions as your summary. There is a Stoic intro assignment that I want you to watch want you to work on to see if this new kinds of conversions is making sense. And then there's also some unit practice problems. They're in the week 9 folder on Schoology. Do the first 18 or so, check the answers, see if it's making sense. Skip around. You don't have to do all of them unless you feel like it's helpful. But even picking 5 random ones, checking the answers is a good way to process today's new information because you get immediate feedback, see if you're doing it right, or see where you're making mistakes and ask for help. All right. Thanks so much for your attention today as we learn more about chemistry and this awesome thing called stoichiometry. See you next time.